Section 3.4 of our work, we are looking at analyzing the second derivative. And what does it mean to analyze the second derivative? All right, so we're going to skip all the first derivative stuff. I mean, we have to take the first derivative to take the second derivative, but we're going to skip the analysis of the first derivative. This is page 180 of the Incredibles book. However, I am doing it a little differently, but I am using the same examples. All right, so this is analysis of the second derivative. Right, that's what we're doing. That's horrible, but it's analysis of second derivative. So first thing we got to do is take the first derivative. So this one, I'm going to rewrite this as x squared plus 3 to the negative 1. Okay, then I use power rule, so it's negative 6. X squared plus 3 to the negative 2 times 2x, right? I'm doing chain rule, taking the derivative of the inside. Clean that up. So I got negative 6 times 2x. That's negative 12x over x squared plus 3 positive 2. Remember, you have a negative exponent, you're writing the denominator as positive exponent. Here we go. Now we're going to take the second derivative. Second derivative, I'm going to use quotient rule, right? It's a fraction. I could use quotient rule up here. In fact, many students argue that quotient rule is easier than rewriting it this way and using the chain rule, all right? But I prefer the chain rule. So I'm going to use the quotient rule here. So bring up the denominator, multiply by the degree of the new derivative of the numerator, minus the numerator, which would be negative 12x, times the derivative of the denominator. So it's going to be 2 times x squared plus 3 to the first power times 2x. The 2x is the derivative of the inside. So this 2 came down. Subtract 1 from that exponent, and then take the derivative of the inside over the denominator squared. It is already squared, so square it again, makes it raise it to the fourth power. Clean that up. So that's going to be, so what I'm going to do is take out an x squared plus 3. There's an x squared plus 3 in common. I'm going to take that out. When I do that, it's going to leave me a negative 12. That's that negative 12. I'm only taking one power of x squared plus 3 out, so it's going to leave another x squared plus 3. So I'm going to go ahead and multiply that. So it's going to be negative 36. All right. And that's going to be a plus 12x times 2x. Remember, I've taken out the x squared plus 3. I've taken it out. So that's going to be 2 times 2 is 4. 4 times 12 is 48. So that's going to be a negative 48 and a positive 48. So it's positive 48x squared. And this x squared plus 3 is gone because it's up front. I factored it out. There it is. Over x squared plus 3 to the fourth. So that means I can reduce the x squared plus 3. So that's going to be 48x squared minus 12x squared is 36x squared minus 36 over x squared plus 3 to the fourth. The third. Let's continue to clean that up. I'm going to take out a 36. So that's going to leave me x squared minus 1. And I still have x squared plus 3 to the third. And that's the second derivative. All right. Now, in order to analyze the second derivative, we need to know when is the second derivative equal to 0. So we're setting this equal to 0. But remember, for a fraction to equal 0, only the numerator needs to equal 0. So I'm going to do 36x squared minus 1. So divide by 36, and I just get x squared minus 1 equals 0. So that means x equals plus or minus 1. All right. Another critical number is if the denominator is equal to 0. Well, that's a candidate anyways. And no, this denominator is never equal to 0, so we don't have anything from the denominator. Excuse me. I'm going to pause the video for a second. Continue. All right. So we are going to use that. Make a sign chart for it. Sign chart says that's a quadratic basically, so it's plus minus plus. If you need help making a sign chart for that, just ask me in class. So this is going to be, so if the second derivative is positive, it is concave up. So it's going to be concave up from negative infinity to negative 1 and 1 to infinity. and it's concave down from -1 to 1. And what are the points of inflection? Well, because the concavity changes at -1 and +1, the point of inflections are at -1 something and 1 something. All right, so all I'm going to do is take the -1 and plug it back into the original function. So if I plug in -1, that's going to give me 6/4, or 3/2. So it's 3/2. And if I plug in 1, I get basically the same thing. So it's 3/2. All right, so those are my points of inflection. So these are my points of inflection. -1 3/2 and +1 3/2. So when we talk about a second derivative analysis, this is what we're looking for. What are the points of inflection? Where is it concave up? Where is it concave down? All right, I'm going on to number 2. It's on page 181, number 2. All right, I think I copied this wrong. I think it's e to the x squared. So it's g prime of x is going to be 2x e to the x squared, right? I'm using chain rule, right? The derivative of e to the something is e to the something, and then you take the derivative of that something. So the derivative of x squared is 2x. When I take the second derivative, I have to use product rule, because now it's 2x times e to the x squared. So take the derivative of 2x, which is 2, keep the e to the x squared constant, plus 2x times the derivative of e to the x squared. I just copied that, because that's what it was. Clean that up. I'm going to factor out a 2 and an e to the x squared. So I take an e2 to the a to the x squared. When I take 2 times e to the x squared out, that leaves 1 there. And if I take 1, 2 out, that leaves me the x's. So that's going to be x squared Really? Is that right? Let's double check this. I just confused myself. All right. So the derivative of 2x is 2. Yeah, that's right. Is this ever equal to 0? No. This is not equal to 0. So 1 plus x squared is never equal to 0. This thing is never equal to 0. It's always positive. So it's concave up. Concave up from negative infinity to infinity. Okay, so you might be wondering, how do I know that? Well, I know that 2 is always positive, right? 2 doesn't change signs. E to the x squared. E doesn't change signs, so that's positive. 1 plus x squared. If you square any number, it's positive. And I'm adding 1 to it, so it's always positive. So this whole thing is always positive. So it's concave up, negative to infinity to positive infinity. There is no concave down. So that's number 2. Number 3. This is page 181. All right, let's take the derivative. So that's x squared minus 4. All right, bring up the denominator times the derivative of the numerator minus the derivative of the denominator times the numerator over denominator squared. All right, let's clean that up so we can take the second derivative. Let's multiply that out. So it's 2x cubed minus 8x minus 2x cubed minus 2x x squared minus 4 squared. 2x cubes cancel. Negative 8x minus 2x is negative 10x. X squared minus 4 squared. All right. That's the first derivative. Now we find the second derivative. So that's going to be x squared minus 4 squared times the derivative of the numerator, which is negative 10. And my pen is dying. Switching pens. So minus negative 10 is plus 10x times the derivative of the denominator. It's 2 times x squared minus 4 to the first power times the derivative of the inside, which is 2x, all over x squared minus 4 to the fourth power. Continuing, there's an x squared to minus 4 in common. So I take it out. That's going to leave me negative 10 times x squared minus 4. So that's going to be plus 40, right? Remember, I took one exponent of that out. So just one left over. So it's negative 10 times x squared minus negative 4 times negative 10 is plus 40. Here, I took out the x squared minus 4. So I have 2, 2, and 10. So that's 40x squared plus 40x squared over x squared minus 4 to the fourth. So this reduces. X squared minus 4 and x squared minus 4 denominator reduces. And I clean up the numerator, so it's 30x squared plus 40 over x squared minus 4 to the third. All right, now, so the numerator is never equal to 0 because there's no way to get a square plus a number equal to 0. Let's double check our signs here. Yeah, that's the correct sign. All right, so then you might think, so this has no critical numbers. That's true. However, when you make a sign chart, you also want to find out where it's undefined. So this derivative is undefined when the denominator is equal to 0. So what I have is negative 2 and 2 on the number line, right? So negative 2 squared is 4, 4 minus 4 is 0. So it makes the denominator 0. Same thing happens when you plug in positive 2. Okay. All right. Now, so what happens? So it's going to be positive here, negative here, positive there. All right. You just check what's left in negative 2. What's left in negative 2? Negative 3. Negative 3 is 9. 9 minus 4 is 5. 5 to the third is positive. Plug in 0. 0 minus 4 is negative 4. Negative 4 to the third power is negative 64. So it's negative. Plug in, say, 4. 4 minus, no, don't plug it. Oh, 4. 4 squared is 16. 16 minus 4 is 12. 12 to the third is a big positive number. All right, so it's concave up. Negative infinity to negative 2. And 2 to infinity. And it's concave down from negative 2 to 2. Does this have a point of inflection? You might think, well, it does change concavity at negative 2 and positive 2. But it does not have a point of inflection because negative 2 and positive 2 is not part of the original domain. Okay, so that's it. This is all we have. There are no points of inflection. And that's long enough for a video. I'm going to continue the other problems on another video. Okay, so put that up. The answer was concave up, negative infinity, negative 2, 2 to infinity. Concave down, negative 2 to 2. No points of inflection. Even though concavity changed, but these are points of discontinuity, right? This has a vertical asymptote at x equals plus or minus 2. All right? All right, that's it.